on the surface of the sphere with some potential which favors hexagonal ordering, let's say. On a sphere, this of course is not possible. There are some topological restrictions, so not all of them have 6 neighbors. So this one, for example, has only 5 ones. And then I view this as imperfections or defects, which have an influence on the elastic properties of the shell, on the surface here. And here, in this example, I modify the bending rigidity of the surface depending on this defect structure. And the bending rigidity is weaker in these points, and that leads to a deformation of the surface. And what we get at the end is this icosahedral type shape, where at all the points where I only have 5 neighbors, kind of high curvature regions form, and all the other regions in between are more or less flat. So that's what I have in mind, and that's joint work with various people from my research group. Now the question is this of interest? And well, the example I just showed you is, for example, found in viral capsides. So here the building blocks are proteins, and well, these capsides are characterized by their form. And what one indeed finds that well, capsides which a large number of proteins typically have this icosahedral type shape, and capsides with small number of proteins typically are spherical. However, one also finds such things for orientational order. So what you see here is a nematic shell, spherical, and here we have different types of defects. Here we have this well, 1/2 plus 1/2 type defects, and one finds 4 of them, and they are arranged in a tetrahedra. Now these are examples. We have seen this experiments already in various other talks. So what the people did here is put microtubules and molecular motors on the surface of the vesicle. And so what happens then is indeed well, an active nematic film on the surface of the vesicle is formed, again with 4 of this plus 1/2 defects. And then due to the activity, this defects oscillate. One can actually tune this, and depending on the properties of the vesicle, also the vesicle deforms and forms these protrusions over there where we have the defects. So there's also this influence on the shape. And the last example is on a larger scale. So think about tissue, an epithelia cell. And we can also interpret this tissue as an active nematic, so just give each cell an orientation due to their polarity, for example. And what people found is that in this 1/2 plus 1/2 defects in this tissue, also the more elastic properties are different, and these are actually sites where more cells get extruded from the epithelium. Okay, now how to model this? Well, it's a general framework. I would like to describe this with continuum theory, coming up with evolution equations on the surface, giving us the ordering, and then an evolution equation for the surface evolution to give us well, changes in the morphology in normal direction, and couple those appropriately. So let's start with positional ordering. So here my model on the surface is a phase field crystal model, where the unknown is rho, it's a particle density. And the energy is such that I have a double layer structure, which gives us 2 minima, particle or no particle. And then I have a gradient term with a minus sign, and the next higher order term, which kind of regularizes this. So this gives us a length scale and the distance between the particles. And then I define a conserved evolution law, H-1 gradient flow for this particle density, and solve this. Now, what does it do in 2D? This gives, well, this one length scale, so we get our hexagonal ordering. Now I formulate this on a surface gamma. So all these operators are the surface operators, the surface gradient and the Laplace-Beltrami operator here. So I automatically get incorporated this topological defect if I do this. Well, and if I solve it for small number of particles, I get this equilibrium shape with this kind of soccer ball configuration with the 12 points which only have 5 neighbors. And if I do this on larger spheres, I can further reduce the energy by introducing additional defects with this grain boundary scar. So now how to couple this to an evolution of the surface. Now I would like to have, in addition to this energy, Helfrich type energy. H is the curvature, and I have a bending rigidity, and this bending rigidity I will make to depend on the variational derivative of my PFC energy. And now, to get a coupled system of the evolution for the particle density and the shape gamma, I have two basic requirements I would like to fulfill. The first one is still conservation of particle density. Now gamma depends on time, so it evolves. So to get this, I have this additional term, with v being the normal velocity and h the mean curvature. So I get this evolution equation for my density gamma. And then the second ingredient I would like to fulfill is energy dissipation. So I parameterize my interface gamma, and with nu being the normal velocity. And now I compute the variational derivative or the time derivative of my energy in such a way that I decouple the two things. So here I have the evolution of the interface, and here I have the evolution of the particle density. And now I simply plug in what I just computed for the time evolution of the particle density. I get this thing, and now to fulfill energy dissipation, the simplest way is to choose the normal velocity in this form with some parameter in front, which guarantees us this. Right? And now I have a coupled system for both. That's the one. Well, there are various coupling terms, so I simplify this a bit. Instead of the full energy, I only take in the first equation the PFC energy, because, well, here I'm just interested in kind of the evolution for the density and the contributions from the Helfrich energy. Well, there will be various things, but they might not be that important. And for the evolution of the surface, so that's more macroscopic thing I'm interested in, here I only take the Helfrich energy and not this PFC energy, because I'm not interested in modulations of the surface on a molecular scale. Right? And then I can solve this numerically. So the way I do this is to reformulate the whole thing in a diffuse interface context, so embed it in R3 and then solve the equation for that. And then here you see various examples with different numbers of particles or dots in maxima in my density field, and you get or coupled evolution for the arrangement of the particles and the evolution of the surface. Okay. Now let's come to orientational ordering, and well, thanks to the previous speakers to introduce the theory. So instead of having now this positional ordering, I would like to describe an director field on the surface. Now, one first has probably to derive the equation. So what we do, let's start with a Frank-Oseen type model, where P is now my director field in this general form. So I can formulate this in R3. And I go to a one constant approximation, as all the others before me as well. And the unity property that the length of P should be 1, I describe only weakly with such a potential. Okay? And now I formulate this in a thin film around my surface with appropriate boundary conditions there, and let the thickness of the surface go to 0. And what I obtain is a model for my director field P, which now lies tangentially to the surface. Okay, that's what I'm interested in. And what I get is well, two different contributions. It's an intrinsic contribution for the energy, where these operators here are now the surface operators on the surface, so surface divergence, surface rotation. And I get an extrinsic contribution where B is the shape operator. And of course my penalization term. And then with this energy I can define a gradient flow, now a two gradient flow on the surface, and what I get is well, this vector valued surface PDE for the tangential director field P, where we have here the Laplace-Derame operator, well, the shape operator, and the penalization term. And now, the question is how to solve this. There are not too many theories around this. So in this paper, we kind of compared 4 different ones we came up with. Well, on a sphere, many people did this. You can use spherical harmonics for doing this. We also introduced some discrete exterior calculus approach where you can directly solve it on the surface. And then the other approaches is to kind of extend it to R3 and penalize all normal components. And then you can write it in a component-wise fashion and use like surface finite elements or again a diffuse interface method for doing this and solve it. Okay, so here's a relatively simple example on a sphere. So we start with putting like 4 defects on the equator, a saddle, a sink, source, and another sink, and let it evolve. And what happens is that well, the saddle and the sink, they come close to each other and annihilate each other, and then the remaining source and sink, they maximize their distance. They all stay on the equator, and we use this to validate our 4 numerical methods. And well, in each case, of course, the topological charges nicely add up to 2, as they should be for fulfilling the Poincare-Hopf theorem. Okay. Now, I can't yet couple it to an evolution of the surface to minimize the energy, but to demonstrate you that we are on the way going there is to formulate it at least on an evolving surface. And let's play this movie. And so it's a, oh, come on. I don't see it here. So I see it there? No. Maybe. I don't have mouse, I'm sorry. Anyhow. Probably I'm sorry, it doesn't work. I mean, that was the highlight of the talk, but but anyhow, what happens here is you have this sheet, and of course all the lines should arrange along the minimal curvature direction, and then you unfold it and fold it in the other direction, and they follow that. I can show you it on the laptop here. Maybe. Well, in order to do this appropriately with the dynamics, well, one should use this Ericsson-Leslie type model. Andreas nicely introduced. Here it would be a simplified form, but formulated on a curved surface with a Navier-Stokes equation on the surface, the Ericsson stress term. So all the blue terms come from the evolution in normal direction, and the equation we just had. Okay. Now, next step is to do this also for pneumatics and account for well, the two different directions. So we would like to do the same for a Landau-deGenne model. Well, again, Andreas introduced this. Here it's a bit more general way of this Q-tensor energy. We have this elastic component and the thermotropic part. Here it's written in 3D with the Q to the power of 3 term. And now we do the same. So we we formulate this in the thin film with natural boundary conditions. They are central. And then let the limit of thickness go to 0. And what we end up with is an energy for a surface Q tensor, again with the constraint that it should be tangential. And we again have well, an elastic part and an entropic part. And well, there are some nice ingredients here. So for example, in the 3D part, you have this Q to the power of 3 tensor, which allows you to have coexistence, for example, of isotropic on a nematic phase. Or in 2D, you don't have this. So essentially, you have a change in phase transition type if you do this. However, now in the elastic components, we have terms like this one or that one, where the prefactor here depends on curvature properties. So what this means is that now the double well you can change locally by geometric factors. And indeed, still in this surface model can have coexistence between isotropic and nematic phase. Okay, and then we proceed in the same way to formulate an L2 gradient flow. Looks very ugly, but still one can proceed in the same way. So extend it to 3D, penalize all normal components, and then solve it component-wise. So that's hundreds of operators you have to implement if you do this, but well, we did this, and here are some first results. So we do this on an ellipsoid, and again put our 4 defects as previously along the equator here. What happens now is that they immediately split into 1/2 defects, plus 1/2 and minus 1/2 defect. And then they move together, and the blue and the red one, they annihilate each other. And then the remaining 4 plus 1/2 defects arrange in this tetrahedral structure, however, such a way that, that they are closer to the high curvature points. And that's what happens. I also have, well, here not included, but I can also demonstrate that there's really a coexistence between isotropic and the nematic phase. But I guess the time is up, so let's conclude here. So what I wanted to demonstrate is that, well, this defects in positional or orientational order can have an influence on the shape evolution. That's ongoing work. So we did this for the case of positional ordering, and for orientational ordering, well, for a Frank-Oseen model, and for a Landau-deGenne model on a stationary surface, and well, everything which has to do with shape evolution is work in progress.
Questions? Yes, please.
So, very interesting talk. One thing is a comment and a question. We've solved the equilibrium shape for a system which has free surfaces and edges. And in that context, I wanted to ask you, when you are calculating the gradients, how are you calculating the gradients? Because when we did it on curved geometries, we essentially did covariant derivatives, and that creates a problem because of the shape and texture coupling. So,
right. So that's well, that's an issue. So there are different ways we do this. So first of all, these are all covariant derivatives you see here. And well, the most direct approach we did, well, not for the Q-tensor model, but for the Frank-Oseen model, is using discrete exterior calculus for doing this. That's one way. And the second way is to say, well, I allow for a representation in R3 and allow also for a normal component. And then I can write it using derivatives in R3, but then we penalize all normal components in the equations.
There was another question.
Yeah, is there any physical meaning to allowing P to be something other than a unit vector, or is that a numerical convenience, or?
Well, I mean, it's a question how to define a defect in this setting. I mean, it's not a very uncommon way of doing this. I mean, to do this limit, right, and to do it on a closed surface, you have to violate either P to be of unity or the requirement that it should be tangential. So you can't fulfill both. And
This is to allow places where P will be undefined or
yeah,
P is
right.
I see.
Of course, kind of the it depends on kind of your penalization here, how large your defects are going to be, and so on. So that should be taken with care. Yeah.
One more, yes.
In your computation, did you try initial data had two defects on the sphere, and then when time evolved, what happened on the defect?
Yeah, we tried various things. So in this publication there, we also demonstrated that well, if you deform your defect, you deform your structure, you can initially, or you can get minimal energy configurations with more defects than two. So we demonstrated this.
When you start with two, degree one
Yeah,
defect,
for the pneumatic.
and then it becomes split into a full degree 1/2 defect. You have minimal energy.
Yeah, that also happens. So if you start with that's not the minimal energy configuration. The two will also split, and you get for 1/2.
Okay, let's thank our speaker and all the speakers.